Hi, everyone. So today we are starting Unit 4, and in this unit we're going to be learning about an entirely new type of function, a function that's very different from polynomials and rational functions. And these are called exponential functions. So today we're basically going to be constructing an exponential function from scratch, and we're going to go through multiple versions as we do so. You will probably see a lot of familiar things. A lot of this video should be review, but exactly how much of it is review will depend on who you are and what class you're taking and what background you've had. So I would pay close attention. Also, we're going to be putting things, even the old things, into our new function language. So there will definitely be plenty of new stuff. All right. So before we start constructing our exponential function, we're going to go over some terminology. This is terminology we've used before, but it's going to be especially important in this new unit that we be able to keep these words straight. So what I have here is an expression, 5 times 2 to the third, and all three numbers in that expression have a different name. Okay. So the 5 sitting out front, that is a coefficient. Pretty much we use coefficient the same way we use it for polynomials, as something that's being multiplied to the entire thing. The 2 is a base of the exponent, and that 3, as before, is what we call the exponent itself. Okay, so we've got coefficient, base, and exponent. The only difference between a polynomial and an exponential function is which of the two numbers we're calling the input variable. So in a polynomial function, it's the base that's the input. So for example, 2 times x to the third. X is the base, right? In an exponential function, we're switching it around. We are fixing the base, and we're letting the exponent be the input variable. Thus the name exponential function. Okay, so something like 7 times 4 to the x that I have down here is an exponential function. Okay, so it looks very similar to a polynomial, but we're going to see that putting the variable in a different place means that these behave very differently than polynomials do. Okay. So as I said, we're going to start constructing this from scratch, just talking about what it is. And like I'm saying, I expect there's going to be a lot of review in the next couple slides, but do pay close attention. So to create an exponential function, we first have to fix the base. We're going to call that base a, and we're also going to fix a coefficient c. So in this example we are constructing right now, we're going to set the base to be 3. And we're going to make the coefficient equal to 1 so that it basically goes away. That's just going to clean things up in our first example. Okay, so we're going to talk about the function f of x equals 3 to the x. And in this first version of the function, which we're going to expand on, the domain of this function is just positive integers. Okay, so we're going back to that domain and codomain language from Unit 1. So our inputs into this function are positive integers, and the output we're saying is any real number. In fact, that codomain will stay real numbers throughout every version. Okay, so think about this as exponents as we learned them in middle school, right? The rule is that you're just multiplying the base with itself that many times. So for example, if I want to plug in 4 into this function and take 3 to the 4, that just means 3 times 3 times 3 times 3, okay, which I guess is 81. All right, pretty familiar stuff, right? Now we can graph this function even as just a function on the positive integers, but it's just going to be a bunch of points. And I actually did that down here. I graphed the first 5 points. Of course there's more, but it just grows very, very rapidly, right? So it was hard to get the scale right so that I could see very many of these points. Right? And notice that this is out of scale. Okay, so pretty simple start, right? And we're going to expand on this by allowing ourselves to take more and more inputs. All right, eventually we want to be able to input any real number into this function. So in version 2, we're going to ask the question, can we extend this to allow not just positive integers, but positive rational inputs? Okay, and we can do this, right? We can take an exponent that is a rational number, but the way to do that is with roots. Okay, so in this second version of the function, our domain is now positive rational numbers. Okay, and the rule is the same as before, at least if you're inputting an integer. But if you're inputting a rational number, then the rule is as follows. Okay, so it's a little bit more complicated. If we're going to plug in 1 over q, well, that becomes the qth root. Okay, so in this example where I have 3 to the x, 1 over q would become the qth root of 3. Okay. What about if we have a numerator that's not 1? Well, if we want to map, or if we want to take an exponent p over q, it's a little bit hard to say this in words, but we map this to the pth power of the qth root. Okay. Phew. All right. Well, it makes a little bit more sense when we see this, when we give examples of this, right? So if I want to plug in 1/4 into this function, in other words, take 3 to the 1/4, then that's the 4th root of 3. Okay, so a number that when you multiply to itself 4 times, you get out 3. All right, and that turns out to be about 1.31, but it's definitely an irrational number. Okay, what about if I want to plug in 5 over 4? Well, according to these rules, that means that I take the 4th root of 3, because the denominator is 4, and we take that to the 5th power because the numerator is 5. And we get out 3.95 in this case. Okay, so I think for some of my audience will remember this and be okay with it. And some of it will need to do lots of practice, and we'll get lots of practice so that this feels familiar. And even if you've seen it before and you've just forgotten some of this stuff, that's okay. We'll make this really familiar. All right, so now that we're allowed to plug in any positive rational number, we get a more interesting graph. And I've tried to do it here, okay, but it's a little bit strange because notice I'm saying rational number. That means that so far I can't plug in an irrational number, right? And that means that this graph that you're looking at here is going to have lots and lots of holes, okay? I mean, irrational numbers are everywhere on the real number line. You can't get away from them. So you just kind of have to imagine that this line that we're looking at has infinitely many holes. Okay. There are rational numbers all over the place, but there are also irrational numbers all over the place. So not really something that Desmos or even me with a pencil can handle very easily. Okay, but let's talk about, could we extend this to allow irrational number inputs? And the answer is yes. Okay, and I'm going to give 2 answers. The short answer to this is just to fill in all the holes that I talked about earlier. Okay, so we're imagining that there's a graph that has a hole at every single irrational number. Well, you just basically plug those all in. Okay, excuse my cat. The longer answer is a number like 3 to the pi. Okay, pi is an irrational number. So what does that mean really? Well, it's the limit of 3 to the x, where x is a rational number, that's approaching pi. Okay, so if I were to do this, if I were to take 3 to the 3, and then 3 to the 3.1, and then 3 to the 3.14, and then 3 to the 3.141. I'm trying to remember the digits of pi, but I actually can't remember that many. Well, what you'd find if you did that, those are all rational numbers that I gave, so you could use the previous rule for that. And then you find that these answers are getting closer and closer to something. And the thing that they're getting closer and closer to is what we call 3 to the pi. Okay, so it's a little weird because it kind of means that 3 to the pi doesn't have like an intrinsic meaning. We just define it to be the limit of something. And that's kind of the best we can do. It still makes sense, and it gives us a nice continuous function, and it obeys all the exponent rules that we're used to. It's just a little bit awkward to define. Okay, but if you like the shorter answer, which is just that we're filling in all the holes, that's also a pretty good way to think about it. Okay, so last step is, what about negative numbers, right? So now we're allowing positive rational numbers, positive irrational numbers. All that's left is 0 and the negative numbers, okay? And the last step, I think, is pretty easy. We can define our exponential function on these. And the way that we do that, well, what is 3 to the 0? That's just always 1. And if we want to plug a negative number in, like 3 to the minus x, we just define that to equal 1 over 3 to the x. Okay. So what that's going to do is it's going to fill in the left-hand side of this graph. Notice, by the way, that I've changed the scale from previous versions of this. So now the graph is extending off to the left, and as it does so, these numbers are getting closer and closer to 0. That's because taking 1 over larger and larger powers of 3 is going to get you closer and closer to 0. So notice, by the way, that this graph actually has a horizontal asymptote on the left-hand side, and that's y equals 0. Okay, I want to say something a little bit before moving on, which is try to motivate. Why are we extending the inputs of this function? Why not just stick with the original function? And the simple answer to this is that if we're going to want to model things with exponential functions, then we're going to want our inputs to be anything. I mean, if we want to model something where the x variable is something like time, then we might want something that works for things that are not integers, if we're talking about decimals of seconds or things like that. So we're creating this function so that we can use it to model things in the real world. And there's going to be plenty that we'll be able to use exponential functions to model. Okay, so there's one more slide left. And that is, I want to talk a little bit about how these functions behave in different bases. Remember that the base is something that we had to fix at the beginning to create the function, right? The base was constant throughout the development of this function because it's not the variable, the exponent is the variable, right? But what happens if we look at different bases? Well, we get different functions with different graphs. And for the most part, these graphs look very similar. Okay, so what I have graphed down here is y equals 2 to the x. That looks very similar to y equals 3 to the x. It's just doesn't grow quite as quickly, right? Because when you take powers of 2, it doesn't grow as quickly as taking powers of 3. Okay, I've also graphed here y equals 5 to the x, and you can see that does grow a lot more quickly. But notice that some of the points are the same, right? Like if I plug in 0 into any of these functions, I get out 1. That's just because of that simple exponent rule that says that anything to the 0 equals 1. And both of these functions do still have that horizontal asymptote on the left. Okay, the last one is very different. So if I plug in something like 0.5 to the x, then actually instead of something that grows, I get something that decreases, right? So the first two are increasing functions. This one is a decreasing function. And that's because as I'm taking powers of 1/2 or 0.5, I'm getting smaller, right? As I take higher and higher powers of that number. Okay. So a pretty simple reason, but it does change the graph. So the graphs of these functions, they have a shape that you're going to want to become familiar with. And the basic shape depends on whether your base is bigger than 1 or less than 1. Okay, I didn't talk about what if your base is equal to 1, but if you think about it, that's pretty simple because 1 to the x is always 1. Okay, now important note up at the top here. Remember that our definition in like version 2 involved taking roots. So if we're going to be taking roots such as square roots, then we can't have our base be a negative number. Okay. I mean, we could in version 1, but as soon as we got to version 2, we're not allowing that because we want our outputs to be real numbers, not complex numbers. So we are forcing that base to be a positive number. base equal to 0 is also kind of not okay because we're taking reciprocals in that last step, and we don't want to be dividing by 0. So we are only going to be sticking with bases that are positive numbers. Okay, so that about wraps it up. Plenty to think about and talk about, and I'd be happy to take your questions on any of this stuff in class. All right, so I hope you are having a great day. I will see you in class.